Now let's consider how vibrations are obtained for a finite system like a molecule. In this case, one has to take account of the fact that translation of the molecule as a whole or rotation of a molecule as a whole do not correspond to the vibrations, and therefore there will be some um, specific combinations of atomic displacements corresponding to translation and rotation, which have to be excluded from the set of all possible displacements of atoms. So, in other words, we have to exclude translation and rotation in order to have only vibrations presented. Um, so, first of all, let's consider translational invariance. For that, we define a momentum of our molecule, which is the sum of all momenta for each atom, and we set it to 0, which would mean that that quantity, which corresponds basically up to the total mass, to the center of mass, is constant. So we can choose its value to be 0. So this would be the first condition which connects the atomic displacements. There's also rotational invariance. For that, we would claim that total angular momentum of the whole molecule is equal to 0. And total angular momentum is defined here. Here's the velocity gain. And this expression can be rearranged a little bit to create a simple condition which connects all the atomic displacements to keep the momentum constant. For that, we consider the case of small vibrations only. This is the case we consider anyway, because we work in the harmonic picture, in the harmonic approximation, when we assume that atomic displacements are small. So in that case, we replace the atomic position Ra with a vector for the atom A, which will be given by this. Ra naught is the position of that atom at equilibrium, at the minimum of the potential energy surface, and UA is a displacement. Because UA is small, we can neglect here the product of UA and UA dot and approximately write the total angular momentum as shown here. And again, because u dot is only here, we can take the time derivative out, and we arrive at that expression that the time derivative of this is equal to 0. And of course, that means that this expression is a constant, and again, as in the case of the momentum, we can choose this constant to be equal to 0. And that would give us another equation. So these two equations, if both are satisfied by the displacements, would eliminate rotations and translations of the system. And therefore, because this provides constraints for the atomic displacements. And therefore, when we consider vibrations of a molecule with 3n degrees of freedom, where n is the number of atoms, we'll have to exclude 3 translations and 3 rotations from the system. So 6 degrees of freedom less we will have in total for left for the vibration. So there will be 3n minus 6 for a nonlinear molecule. In the case of a linear molecule, for example, a hydrogen molecule, this number will be 3n minus 5 because one rotation around the axis of the molecule actually doesn't lead to any rotation, so there will be vibrations associated with it. Okay, so these are two conditions, and now I will demonstrate to you how this can be taken into account in two examples. One example would be a linear molecule like this, with 3 atoms, 2 identical atoms with mass m, and 1 atom in the center, in the middle between the two, of the mass capital M. Both at the distances are r naught. We will consider this case, and also we shall consider the case of a water molecule here to demonstrate how now vibrations can be found for these kind of systems. In both cases, we shall assume that we know the potential energy of the system in a simple form, and as we discussed before, these potential energy expressions can be worked out using say ab initio calculations by training a set of analytical expressions and then using these analytical expressions, or just using some other means. But in this case, we just assume that very simple potential energy expressions, and from this you will get an idea how shall we deal with these two conditions in practice. So let's start from this example of the linear molecule. And we shall assume that the potential energy is rather simple. So you have a harmonic term connecting atom 3 and 2, and you have another harmonic term connecting atom 1 and 2. We don't have any direct interaction between atoms 1 and 3. And for simplicity, we also assume that atoms can only move along the x-axis. So it's a one-dimensional case. As this case is one-dimensional, we can only use the translational invariance along this direction. However, rotations become meaningless, so we don't use rotations in this case. How many degrees of freedom we should have here? Because each atom has just a single degree of freedom, it can move only in the x direction. We have to apply a single translational invariance along this direction. So this would be 1 degree of freedom less. So instead of 3, we should expect just 2 degrees of freedom responsible for the vibrations, or available for the vibrations. So we would have 2 vibrational frequencies and 2 normal modes. Okay, how shall we find them? Let's write this equation explicitly as shown here. So x1, x3, and x2 are displacements of atoms, 1, 2, and 3, from their equilibrium positions. The potential energy is already written via displacements. Okay, and what we can do with this equation, we simply can eliminate 1 degree of freedom. For example, we can eliminate x2. So we then proceed in the following way. We have to introduce 2 other coordinates which would replace these ones, and which would serve as vibrational degrees of freedom. So the simplest choice is to choose x1 plus x3 and x1 minus x3 as these two degrees of freedom, two generalized coordinates. Using these 2 equations, and also this equation here, which relates x2 with x1 and x3, you can relate each of the 3 coordinates, displacements, to these only 2 coordinates. So these 3 equations allow for arbitrary displacements of atoms 1, 2, 3, subject to that condition, which basically keeps the center of mass of the system intact. So the next thing what we need to do is to replace the kinetic energy and the potential energy of our system, which are expressed via the actual coordinates of the system. So this is the potential energy, which is expressed via actual displacements, and this is the kinetic energy, which is also expressed via the actual displacements. But we would like to express them now via these new coordinates xa and qa and qb. We can do that easily by simply using this expression. So we take those and replace them here and replace them here. So you can easily see by doing this very simple math that kinetic energy would be given by these 2 terms, yqa and qb, and the potential energy via these 2 terms, again via qa and qb. So the total Hamiltonian of the system is the sum of the kinetic and the potential energy, and if we sum these 2, you can see that these coordinates qa and qa dot, qb and qb dot, they're completely disentangled, and so the Hamiltonian is the sum of 2 terms, HA and HB, each of those composed just from one particular coordinate. And because these terms, each of those, correspond to the Hamiltonian of a harmonic oscillator with a particular force constant and the particular mass, one can write immediately how these QA and QB coordinates, generalized coordinates, depend on time, what is the frequency. And the frequencies follow immediately as this and that. So then we know that QA and QB are harmonic displacements. So we can, for each of those, we can write what actual coordinates are, and we can build normal modes. So in order to build normal modes, for QA, for instance, we set QB coordinate to equal to 0. So there's no, so only QA mode is excited. And if we do this, you can see that QB is 0. So X1, X3 move in the same direction, but X2 moves in the opposite direction, and there's a prefactor to it. So if the mass in the center much larger than the masses of atoms, these blue atoms, but that coefficient is very small. So with that mode, QA mode, we have this first and the third atoms moving together, synchronous, to the left and to the right, but the central atom moves by a small amount in the opposite direction to keep the center of mass at the same position. Similarly, for the other mode, this time we set QA equal to 0. Then you see that the central atom will not move at all because X2 is 0, and the X1 and X3 move in the opposite direction. So this term is 0, so X1 is half of QB, X3 is minus half of QB. So they move in and out of the central atom. So these are two vibrational modes for this molecule. And of course, when you consider this problem classically, the actual vibrations of the system, depending on the initial conditions, would be a linear combination of these two modes.